Good afternoon and welcome back to Thermal Live 2019. I'm Jennifer Arroyo with Electronics Cooling here in Philadelphia. As the producers of Thermal Live, we'd like to thank you for joining us today. In just a moment, you'll hear from Christian Miraglia, Applications Engineering Manager at Fuji Poly and veteran speaker at Thermal Live. Christian will discuss compression characteristics of thermal gap filler pads, giving you a better understanding of what basic analytical techniques and tests can be performed to understand stress as well as defection in both gap filler pads and PCBs. This presentation will last around 35 minutes and be followed by a quick 10-minute Q&A session. We want to hear from you, so please locate the Q&A panel on your screen and submit as many questions as you'd like. Christian will answer as many of those as he can during the 10-minute Q&A session. If you'd like a copy of this presentation, downloadable slides are available under the Resources tab at the bottom of your audience console. Now, without any further delay, please welcome Christian.
Thanks. First, I'd like to thank everyone for joining us on this webinar. My name is Christian Miraglia, and I'm the Applications Engineering Manager at Fuji Poly America. I'm based out of our Customer Engineering Resource Center here in San Jose. For those of you who have not heard of Fuji Poly, we're probably best known for a line of thermal gap filler materials. We have various types of thermal gap fillers suited for different applications. We specialize both in high conductivity materials as well as lower conductivity, cost-effective materials. Our thermal gap fillers come in various form factors from viscoelastic materials, putty pads, as well as form-in-place thermal gap fillers. One of the biggest challenges working with a thermal interface, and thermal gap filler specifically, is the stress created by compressing the thermal interface. All thermal interface materials require some pressure to work, but thermal gap fillers have a unique challenge. A thermal gap filler is designed to fill a gap that can vary due to tolerance. This means variation in compression and force. This variation in compression equates to different stresses, sometimes not enough stress, but oftentimes just not enough compression. The concern with stress is not necessarily with the pad itself. The pad itself will continue to act as a thermal transfer medium, even at higher percent compressions. Rather, the issue is stress and strain in the PCB, and basically what kind of damage can occur if you overstress the PCB. In this webinar, we'll discuss the characteristics of gap fillers and look how that impacts the PCB. Our webinar is only about 35 minutes, so we won't have time to go too deep in all the concepts, but we hope to give you a better understanding of what exactly is happening when a gap filler is compressed onto a PCB. Before we start, I would like to do a quick overview on the topics we will be discussing. First, we'll look at the compression characteristics of various types of gap fillers, from standard viscoelastic materials, putties, as well as form-in-place. We'll look at some stress-strain curves and relaxation over time. You might be wondering why we would look at a stress-strain curve of a viscous material. The reason is because no gap filler is 100% compressible. Even a dispensable material is going to have its limits. Generally speaking, stress-strain curves are not linear, and gap fillers are typically highly dampened, so compression or stress created by compression is highly dependent on the speed that they are compressed at. We'll look at one critical aspect of the thermal solution, and that is the surface the gap filler is compressed onto. And in most applications, that will be the PCB or component, and the heatsink or heat spreader. Heat spreaders and heat sinks are typically rigid surfaces made of aluminum or some other metal, but PCBs are very flexible and deform quite easily. We will look at how the deflection impacts the overall compression of the pad itself. We'll create a basic stack-up of a gap filler and PCB. We'll look at how the individual deflection and compression characteristics impact the overall compression. We will create a basic model to help us better understand and possibly control stress as opposed to just trial and error. It won't be anything complicated, but keeping in mind the factors that make up compression early on in the design will help you if having to go back and do any type of redesign on the thermal solution. Finally, we'll get some suggestions for managing the stress created when implementing a gap filler onto a PCB electronic assembly. Whenever we discuss thermal interface materials, it's always good to define what exactly is a thermal gap filler. Thermal gap fillers are a thermal interface, but they're unique from something like a phase change or a grease. In the case of phase change and grease tims, these are basically designed to reduce contact resistance only. A thermal gap filler is designed to fill in a gap that can vary due to tolerance. This means actual stress created during the compression can vary, and in most cases can be higher than desired. Gap fillers are typically not used in applications with a fixed force like a spring-loaded heatsink. They are used in applications where there is a gap. The gap is controlled, and there is some tolerance based on the component and assembly tolerances. The actual load or stresses are dependent on the actual gap filler used, specifically the starting thickness. General rule of thumb is the higher the conductivity, the less compliant the gap filler. That being said, gap fillers can come in a variety of form factors, but all have some limitation and characteristics that should be understood. Generally speaking, thermal gap fillers come in three types. The softest of these are the dispensables, or what are also called form-in-place materials. So form-in-place materials are an attractive option because they're essentially a fluid or a viscous material. They create virtually no stress. I say virtually no stress because even they have their limits as how far thin you can go. These dispensables can come as a curing or non-curing type. Curing types are essentially one or two parts, and they either cure at room temperature or they can be cured at a higher temperature to reduce the cure time. Customers are responsible for the mixing in the case of a two-part and for the dispensing. Dispensable gap fillers require equipment and procedures put in place to ensure the form in place is cured properly, if it is a curing type. Some materials don't require curing. Dispensing procedures must ensure no air is trapped in the material and that the correct dispense shape is created before assembly to ensure even contact. One popular dispensing shape is what's referred to as a Hershey kiss. This dispensing tip starts off close to the surface and lists as it's dispensed to apply what exactly looks like a Hershey kiss. Of course, the actual geometry of the dispensable material will depend on the application. There are also current limitations on the conductivity of dispensable type gap fillers. Another popular type of gap filler is what's referred to as a putty or a putty pad gap filler. These gap fillers come in a pad form, so no need for any special equipment. These pads come in a specified thickness, and because they are already formed, there's no concern with air trapped inside like you would have with a dispensable material. They are more of a viscoplastic material. They tend to have a very small to no elastic component. This means there's no bounce back. The plus side is it can be pressed well beyond the 50% mark as opposed to some viscoelastic materials. The most common thermal gap filler are the viscoelastic types. These types come in a variety of thermal conductivities from lower cost-effective materials to high conductivity materials above 10 watts per meter Kelvin. They are often characterized by their ability to bounce back. Lower performing materials tend to retain their viscoelastic properties that we think of when we think of basically silicone rubber. They will bounce back up to a certain point, but keep in mind these materials are very highly dampened. If you made the decision to use a thermal gap filler in your design, the data sheet is typically where you'd want to start. Data sheets will typically have a stress strain curve or some stress strain data in a table or modulus value. Oftentimes this data is only for one thickness. Stress strain will change with the thickness. Thicker materials tend to be more compliant. The thicker you go, the more area there is for the material to deform. Another key point to bring up about the stress strain curve is that they are not linear, at least not for the range of compression most customers are working in. Other factors to be considered when looking at a data sheet is the rate of compression. Gap fillers are highly dampened, so the rate of compression will play a big part on the peak stress. Stress is at its highest when the pad is undergoing compression and begins to relax immediately after. Communicating this to the manufacturing team is very important. Boundaries also play a big part. Compression testing often uses plantons that are the same size as the gap filler. This means the material will deform and will be forced outside of the load path. If the surface compressing the pads are larger, then the pad will require more force to get to a given compression. This is one reason you will find that the data sheet varies from the actual. You want to have a good understanding how a thickness, compression speed, and relaxation over time plays a part in the stress on the PCB, especially when you're looking at very sensitive devices. So let's look at some stress strain curves for some typical thermal gap filler materials. On this slide, we can see the stress strain curve of a thermal gap filler. On the right, you can see the plantons used to perform the compression testing. As I mentioned previously, the plantons are the same size as the pad. There's nothing wrong with this test. It's an actual ASTM test, specifically ASTM D575. But unless you have an application where the top and bottom surfaces are the same size as the pads, you will see the stress strain curve diverge, typically about 30 to 35% compression. This is due to the fact that the gap filler in your application will remain in the load path and will require more force to get to a given compression. Something else about the stress strain curve is the fact it's not linear. So using a single modulus value to describe the compression will often be inaccurate. You want to know where on the stress strain curve you will be working. Compressing beyond that point will cause the gap filler to densify and cease to flow. At this point, it's essentially a rigid material. Previously, we mentioned that form-in-place gap fillers are very popular because they do not create too much stress. They are a great option for very sensitive devices or assemblies that require very low stress. The stress created by a form in place is often negligible. They are polymer-based, usually silicone or some other synthetic polymer base, but they are not cross-linked or have very little cross-linking, so they have no tensile strength. The viscosity is what basically holds everything together. They will easily flow as they are compressed, but even these materials are going to have their limits. In the graph, we started with a 1.5 millimeter gap and compressed our SPG form in place with the goal of compressing it as much as possible. You can see the material does flow under compression and gives us little to no stress, but at some point, the stress climbs dramatically. We can never totally compress it down 100%, obviously. In fact, you can see that well before that, the stress climbs dramatically. Form-in-place materials are very easy to compress, but the fillers will eventually act as a hard stop. For TIMs like grease, the particle size tends to be much smaller. This is why you can go to very thin bond lines with materials like thermal grease. Unlike gap fillers, the limit to how thin you can go has little to do with the original thickness you start with. Most form-in-place materials will specify how thin you should go. It is important to know the limits of these form-in-place materials. Form-in-place materials may give the impression they are essentially totally compressible down to almost no bond line. This is not the case. Using them in an application that is very sensitive to stress and compressing it beyond the point where the particles are bottoming out will lead to damage to the PCB and the components. Another characteristic of gap fillers is the compression rate dependency and the stress created. It is probably one of the most overlooked characteristics of a gap filler. There is a tendency to just focus on how much the pad is compressed and ignore the rate at which it is compressed. Quite often the compression rate is uncontrolled. Basically, gap fillers, both putties and viscoelastic pads, are highly dampened and will create different stresses based on the compression speed. In the graph we have plotted, we have the stress strain of the same pad type and size, but at different speeds. You can see that the forces can vary dramatically. In a lab environment, keeping the compression speed low might be okay, but in a production environment, that might not be an option. One of the first things we ask customers when they comment on stress created during compression is what speed is the pad being compressed at? Is it controlled? If it not, can it be? If it is controlled, can we slow it down? Slowing the compression down usually fixes the problem, but in some cases, it is difficult to control the rate of compression. Any procedure changes to address this usually means slower throughput for the manufacturing team. Another option is using a fixed load to compress the gap filler. Gap fillers under a given load will creep. The creep in viscoelastic materials is reversible to a certain extent. There is some compression set, and the amount of set will depend on the type of gap filler. Putty gap fillers have a creep that is not reversible. The compression set is essentially 100%. Putty pads are not reworkable. Once they are compressed, they should not be reused if there is some rework. Even viscoelastic pads should be replaced if there is service required. Because compression is so critical in a gap filler application, reusing even a viscoelastic pad can mean under compression, since the compression set becomes worse over time and temperature. A system that applies a fixed load is basically a fixture with a given weight that applies a load that won't exceed the maximum load the assembly can tolerate. Sometimes having multiple assemblies in the fixture at the same time will help to reduce the overall time. Either way, this solution often means more time for manufacturing. Another way of looking at the rate dependency characteristics is a stress relaxation at a given gap. Sometimes this data is available from the gap filler manufacturer, either on the data sheet or as supplemental data. The graph on the screen is a stress relaxation over time. Unlike creep where the load is fixed and we are looking at how much the gap filler compressed under that load over time, with stress relaxation we are looking at how much the gap filler relaxes over time at a given gap or percent compression. From the graph you can see typically that at about 1 minute the stress has dropped about 12%, and this is going to vary from one material to the other. The force will continue to drop after 1 minute and typically begins to stabilize at 24 hours. Now, we don't require or suggest waiting 24 hours, but applying a fixed load and waiting 1 minute or two will help as opposed to compressing the rate at a fixed rate, and certainly better than an uncontrolled compression. Important to remember the forces are highest during the compression and generally relax once there is no longer any further deformation. Managing the compression from initial to the target percent compression is critical in ensuring the assembly does not undergo more stress that will cause damage to the PCB or solder joints. We spent some time discussing the compression characteristics of thermal gap fillers, but in all our discussions we consider the compression surface rigid surfaces. Basically, metal platens that would only deflect under very high loads, far above the loads that are produced by a gap filler material under compression. Of course, if we are interested in the compression characteristics of an elastomer, we want to make sure we are not introducing deflection from the test system itself, But the reality is that most gap fillers are compressed onto a PCB, and PCBs are very flexible. In fact, many customers are surprised at how easy it is to deflect a PCB, and fortunately, how much it can deflect without breaking. PCBs, in most part, except for specialized PCBs for microwave applications, are made of a woven fiberglass and epoxy resin. Mechanical properties can change based on the supplier, but generally speaking, an FR4 PCB can bend quite a bit before you reach that yield point. The details on how and when a PCB will break are beyond the scope of this webinar. Your PCB supplier would be better suited at answering those questions, specifically on flexing and yield strength. In the case of this test, we'll decide to illustrate the flexing by doing an application-specific test to see how much a single FR4 board will deform. This is something a customer can easily do as well. For this example, we had PCBs made using FR4 that is 0.60 thick, about 1.5 millimeters, and a standard half-ounce copper ground plane. We did not populate it with components. In this case, we're just focusing on the deflection of the PCB only. The components are obviously the critical part of any PCB, but the type of components and layouts can vary from one application to the other, so it was very difficult to standardize. There's always concern with localized stress on the solder joints. We often find the deflection of the PCB plays a big part in solder joint failure. The rigid solder joints cannot flex along with the very flexible PCB. This creates stress strains that can be difficult to predict, even with advanced modeling. In this experiment, we did a basic 4-point test. The PCB is held by standoffs spaced at 100 millimeters by 100 millimeters. We use a 27 millimeter by 27 millimeter platen to act as a sort of dummy component. We record the stress strain similar to how we tested the gap fillers in the previous slides, with forces along the y-axis and deformation along the x-axis. In this case, we targeted about a 2 millimeter deflection. We certainly could have deflected it further without actually reaching the yield point. We felt a 2 millimeter deflection is good enough for illustrating the amount of deflection you're going to see in a printed circuit board. As you can see from the stress strain curve, the PCB flexes quite a bit. The curve is linear, at least up to here, and it doesn't look like we're anywhere near close to damaging the PCB itself. With only about 90 newtons, or about 9 kilograms of force, we get up to about a 2 millimeter deformation. In a gap filler application, the compression is a stackable, a flexible PCB, and a compliant thermal gap filler. The question may be, is this too much force? Well, it's not something we could definitely say it's okay, but we want to understand how the deflection characteristics of the PCB react to a gap filler. When we are working with a thermal gap filler, the idea is to compress the gap pad, not the PCB, but in some cases, or at least in the case of this PCB, it's totally unavoidable. So now let's take a look at the pad we're intending to compress onto the PCB. And let's look at its compression characteristic on a rigid surface, just like you would get if you compressed it using an instrument tester, or if you called us here at Fuji Poly and asked us to do a compression test. Basically, a compression curve of the gap filler onto a rigid surface. We're using the same size and compression speed as a PCB test. We can see right away the curve is not linear, as we mentioned before. We have essentially two gradients. One is from 0 to 0.5 millimeters, then a sharp rise from 0.5 millimeters to 1. If we compress it further, the gradient would increase even further as the pad begins to densify. We are not too interested in compressing further. In our PCB example, the PCB deflected 2 millimeters with only 90 newtons. We can see from the graph we don't get much deflection at 90 newtons on the gap filler, so it will be a moot point to go any further. Now that we know the individual compression curves for the PCB and the pad, we can see what happens when we compress them together. Again, conditions are the same. We test the same size pad with the same platen at the same speed. When we do a compression test on the stack-up, you can see what will be quite a bit of a deflection, even though the force is not very high relative to the gap filler. What we are seeing is a very flexible PCB compared to the gap pad will dominate. So the pad is undergoing very little compression, but the PCB is still flexing quite a bit. It's almost like the gap filler itself is quite rigid. This means we're not getting down to the target compression that we intended. Not getting to that target compression is not a big concern unless there was a specific thermal resistance at a specific percent compression, but deformation of the PCB is the primary concern. On this slide, we can see the compression stress strain curve for the PCB, the gap pad, and a stack-up of both. The stack-up doesn't look much different than the PCB alone. Relative to the PCB, the gap filler is almost rigid during compression. The PCB deflection won't be permanent in this case. We mentioned earlier that gap fillers will creep under load or exhibit relaxation at a given gap. This means the PCB will return somewhat. How much and when will depend on the gap filler's relaxation characteristics. For some gap fillers, it may not relax at all. In some cases, it may come close to, but unlikely the PCB will return to its original position. If you know the relaxation loads for the pad, you can match it up to the PCB and get the actual final resting point for the PCB. For example, if you know the pad after 24 hours will go from 150 to 50 newtons, you can figure out just where the PCB will finally rest at. Of course, this could be avoided somewhat. Planning and ensuring the standoffs are closer together will provide more support for the PCB. So we decided to try this again. This time we moved the standoffs to a 50 millimeter spacing. For a very simple test, this was easy to do, but if you have a populated PCB that is ready to go into production, this might not be an option. Boards are packed with surface mount components and traces that are designed to maintain signal integrity at higher frequencies. Laying out a PCB is a time-consuming process. Sometimes it's not as easy as moving a BGA over 10 millimeters to accommodate a through hole, or writing a trace around to allow for a post to be inserted. This is why it's really important to identify components that will require thermal gap fillers and ensure they can support the compression of the pad. In the previous example, the standoffs were 100 millimeters by 100 millimeters apart and gave us a 2 millimeters of deflection with only 90 newtons of force. This may seem extreme, but standoffs that are even farther apart are not uncommon, nor is having a PCB flex as much as 2 millimeters or more. So we ran the same test on that PCB with the closer standoffs. Again, it's 0.60 thick, about 1.5 millimeters, and a 1/2 ounce copper plane. We used the same plant and size, same rate of compression. Decreasing the spacing had a marked impact on the deflection of the board. The PCB under 700 newtons, or about 70 kilograms, now deflected 2 millimeters. If we get the standoff even closer, the boards will deflect even less at a given load. Ideally, we would like to see the deflection be 0, but that's just not possible. On this slide, we could see both the 100 millimeter by 100 millimeter PCB standoff sample, as well as the 50 millimeter by 50 millimeter PCB standoff. Big difference. The forces required to deflect the PCB is now a fraction of what it was previously. I need to bring up an important point though. This doesn't mean we can simply create standoffs that are close together and apply as much force as we want. The PCB is still under a lot of stress. So are the solder joints. The standoffs are also under a lot of stress. So basically anything in the load path is going to be strained. Managing the deflection on the board is critical. That starts with understanding the characteristics of the PCB and the thermal gap filler. As you start to understand the deflection and compression characteristics of the PCB, we can perform some basic analysis on the stack-up. We can do this by creating a spring and dashpot equivalent of the PCB and gap filler. The spring and dashpot are very common when analyzing viscoelastic materials. The spring component is the elastic component. This represents the constant stress created during deformation. For example, a rubber band, or as the name implies, a spring that is stretched or compressed. The dashpot represents the viscous or rate-dependent component. When we discussed gap fillers earlier on in the webinar, we talked about relaxation and how the speed at which we compress the gap filler will impact the stress created. This is represented by the dashpot. A single dashpot and spring, as seen here, is a Maxwell model, but there are other models that use the same dashpot and spring model. All of them are suited for understanding the behavior of different types of materials. We can also look at them in parallel for constant loads to get a better understanding of the creep of an elastomer, while the Maxwell model is better suited for understanding the stress relaxation for a given strain, similar to how a gap filler is used. Unfortunately, the compression characteristics of a gap filler can be a little complicated. Thermal gap fillers are polymers that are highly loaded with fillers. The movement of the fillers, along with the viscoelastic and viscoplastic behaviors of the polymer, make them difficult to model accurately. In some cases, though, generalizing them as a simple spring and dashpot is usually good enough to get a good understanding. So if we look at the components of our PCB and gap filler stack-up, we see that they are quite different. In the case of our PG25A, which is a very soft gap filler, the elastic component is quite small, but there is a large viscous component. What that means is the force required to compress the gap is higher than the force created when we keep the pad in a deformed state. In the case of the PG25A, the force created by the pad in the deformed state is less than half of the force to compress the pad down to a given rate. In the case of our standard rate, which is about 5 millimeters a minute. Of course, increasing that rate just means more stress. The PCB, on the other hand, is almost all elastic, at least as far as we're concerned. The rate of compression will not have an impact on the stress created. This doesn't mean that it is 100% elastic, but we can say at the speed that we're working at and we're assembling at, and there is no oscillation, this can be ignored. If we want to know how the PCB would react under very high vibration, we would certainly want to know what that is. In the case of our PCB gap filler stack-up test, we would look at it as a series of dash spots and springs. If we were to give these components values, the compliance of the PCB would definitely dominate. The PCB would flex under much lower loads. The gap filler's time-dependent component would mean it would require much higher force to compress compared to the PCB. In this case, the PCB elastic component would be reacting to the rate-dependent component of the gap filler. Of course, since the rate dependency means the force will eventually relax over time, it will balance out with the elastic component. If you are inclined, you can create a nice differential equation that describes the relationship of stress, strain, and time. If we look at the compression curves we saw previously, we can see how the individual components impact the overall compression of the stack-up, with the PCB having a high elastic component and the gap filler having a high dashpot component, representing the rate dependency of the gap filler pad. This method of analysis is a helpful way of looking at the stack-up. The downside is that the data required to create a detailed model is usually not available on a data sheet, and even for us to manufacture it, it's difficult to characterize in detail. Visualizing or having a relatively good approximation is still better than trial and error. The takeaway from here is that the compression of a gap filler in PCB is not just a matter of a stress-strain curve on a data sheet. As we discussed earlier, the compression of the gap filler is not linear and highly rate-dependent. The PCB, which is often ignored until there is some failure, is not rigid. In a real-world scenario, the gap filler is in an assembly is not compressed anywhere near the target percent compression. Sometimes you may even think of the force required to compress the pad was less than what was published on the data sheet. But what is happening is the PCB is simply flexing, giving you the impression the pad is deflecting under less load than anticipated. A difficult thing to observe when your assembly is enclosed, and there is no way to visually see that. Something else you can do is to look at the stack-up as a sort of pseudo-spring constant. I say sort of spring constant or pseudo-spring constant because in this case, we're lumping together the rate dependency and the elastic component to one constant. To do this, we have to know the rate of compression, but that is easy to do with the datasheet value. And if you can get a spring constant for your PCB assembly, you can create an equivalent spring constant for the entire stack-up. The spring or K value of the PCB can be one value or constant since it is linear, but the gap filler will be some function. You can add the compliance of the two and create a type of superposition where the sum of the compliance gives you the overall or equivalent stress strain. In our example, the PCB was just so much more compliant than the gap pad that we would not see much of a difference. In a different scenario, the sum of linear constants of the PCB and the nonlinear curve of the pad would give us an idea of what compression actually would look like. We discussed both elastic characteristics and rate dependency, but I did want to dedicate one slide to the rate dependency of the gap filler. We find this overlooked or not understood. One big takeaway is the compression of the gap filler, or the stress created during the assembly and compression of the pad, can be managed by the speed at which the gap filler is compressed. Often, reducing the rate of compression will substantially reduce the stress. The faster you try to compress the pad, the more force you will create. This is a very important thing to keep in mind. The pad will relax and the PCB will bounce back at the point, but the damage may already been done. The datasheet should have relaxation data. You may see this as a curve over time at a given percent compression. This can also be forces after 1 minute, 5 minutes, 24 hours, etc. The relaxation force is an indication of how soft the pad can be. If you see that the force after 1 minute at 50% is much lower than the force at 50%, then there's some room to reduce the stress by simply reducing the rate of compression or using a fixed load that will compress the pad to a given gap over time. If the forces are equal, usually an indication that the material is highly elastic. If that is the case, controlling the speed won't do much for reducing the stress. Gap filler materials usually are not highly elastic relative to the rate dependency component. In fact, if you take a viscoelastic gap filler and compress it with your fingers, you'll see it will slowly return to its original shape over time, but that may be several minutes. Putty pads, on the other hand, won't bounce back and are more viscoplastic than viscoelastic. Either way, they will still have a rate dependency, and a putty pad that is compressed quickly will be difficult to differentiate from a non-putty pad. Managing stress and strain is critical when using a thermal gap filler, especially gap fillers that are higher conductivity. This is due to the high level of loading that makes them just less compliant. One of the best practices is to identify components early on in the design, preferably before the PCB is laid out. Once the board is populated, placing through-holes for support can be difficult or require big changes to the PCB layout. When you have selected a pad, try to get a good understanding of the compression characteristics of the pad. At our engineering center, we do offer testing of pads at the specific size, boundary conditions, as well as the rate. This data is very helpful to understand the stress created during assembly and the stress over time. Creating standoffs and supports around the components that will require a high-performing gap filler is always a good idea. This is the simplest way of reinforcing a PCB. Failure of the PCB is not solely due to the solder joints. Solder joints are rigid, but PCBs are not. Having something rigid solid onto a substrate that will flex means something will fail if the deformation is more than what the solder joint can handle. That concludes our webinar. I would like to thank everyone for joining us. We do have some time for some Q&A, and I'll be happy to answer any questions.
Thank you, Christian. Audience, now it's time for you to enter your questions into the Q&A panel.